On April the 6th, 2026, 4 human beings flew farther from Earth than any member of our species has ever travelled. 252,756 miles. That number surpassed a record that had stood since 1970, set not by a mission of triumph but by a mission of survival. Apollo 13, the crippled spacecraft that swung around the far side of the Moon on a desperate trajectory home. For 56 years, no one went further, and when someone finally did, they did it in a spacecraft that NASA knew, before it ever left the ground, had a damaged heat shield. That is not speculation. That is the documented, verified reality of the Artemis II mission. A mission that is, at this moment, still in flight. A mission carrying the first woman, the first person of color, and the first non-American ever to leave low Earth orbit. A mission using engines built for a space shuttle program that ended 15 years ago. A mission that costs $4.1 billion every time it leaves the pad. And a mission that some of NASA's own engineers publicly stated should not fly. This is the story of Artemis II, what it accomplished, what it risked, what it revealed about the state of American spaceflight, and why the phrase "going where Apollo couldn't" is both factually accurate and deeply incomplete. Because Artemis II did go where Apollo could not. It travelled farther. It communicated 5,000 times faster. It carried computers with 128,000 times more memory. But it also could not do something Apollo did repeatedly: land on the Moon. And the reasons for that gap tell you more about the last 50 years of spaceflight policy than any single mission ever could. We need to begin with what Artemis II actually is, because the mission profile is unlike anything that has flown before. Artemis II is the first crewed flight of the Space Launch System rocket and the Orion spacecraft. It launched on April 1st, 2026 at 6:35 p.m. Eastern Time from Kennedy Space Center's Launch Complex 39B, the same pad complex that once sent Apollo missions to the Moon. It carries 4 astronauts on a 10-day figure-8 trajectory around the Moon, not into lunar orbit, around it. A free return flyby that loops behind the far side, reaches a closest approach of roughly 4,000 miles above the lunar surface, and then swings back toward Earth. The splashdown is expected on April 10th in the Pacific Ocean off the coast of San Diego. The mission is comparable to combining Apollo 7 and Apollo 8 into a single flight, the first crewed test of the vehicle and the first crewed journey to lunar distance done simultaneously. No Apollo mission attempted that. Apollo 7 tested the command module in Earth orbit. Apollo 8, 2 months later, went to the Moon. Artemis II does both at once, with a spacecraft that has never carried humans before. The crew is a deliberate statement. Commander Reid Wiseman, a 50-year-old retired Navy captain and former chief of the astronaut office. A widowed single father who becomes the first person to command a lunar distance mission since Gene Cernan stepped off the surface in December 1972. Pilot Victor Glover, 49. A Navy captain, an F/A-18 test pilot who flew on SpaceX Crew 1 to the International Space Station. He is now the first black astronaut, the first person of color of any background, on a mission beyond low Earth orbit. Mission specialist Christina Koch, 47, an electrical engineer who spent 328 consecutive days on the space station, the longest single spaceflight by a woman in history. She participated in the first all-female spacewalk. She once wintered over at the South Pole. She is now the first woman to fly to the Moon. And mission specialist Jeremy Hansen, 50, a colonel in the Royal Canadian Air Force and CF-18 fighter pilot. He has never been to space before. This is his first flight, and it is taking him farther from Earth than any human being has ever gone. He is the first Canadian, and the first non-American to leave low Earth orbit. His seat exists because of a 2020 treaty between the United States and Canada, exchanged in part for Canada's commitment to build the Canadarm3 robotic system. 4 people. The first 4-person crew in deep space, every one of them making history by being aboard. The vehicle that carries them is the most powerful crewed rocket ever flown. The Space Launch System, in its Block 1 configuration, stands 322 feet tall, weighs 5.75 million pounds fully fueled, and produces 8.8 million pounds of thrust at liftoff. That is 15% more thrust than the Saturn V, the rocket that sent every Apollo crew to the Moon. 2 5-segment solid rocket boosters built by Northrop Grumman that provide more than 75% of that thrust during the first 2 minutes of flight. Each booster stands 177 feet tall and generates 3.6 million pounds of force. The core stage, built by Boeing, is 212 feet long and powered by 4 RS-25D engines, the same engines that once powered the Space Shuttle. Serial numbers E2047, E2059, E2062 and E2061. That last engine was a late substitution, swapped in during April 2025 after the original unit developed a hydraulic leak in an oxygen valve. These engines were designed to be reused across dozens of shuttle flights. On the Space Launch System, they are used once and dropped into the Atlantic Ocean. The first 4 Artemis missions each use 4 of the 14 remaining RS-25D engines from the shuttle inventory. After those are expended, NASA will transition to newly manufactured RS-25E engines at a cost that has not been finalized. The solid rocket boosters, too, are fully expendable, unlike the shuttle-era boosters which were recovered by parachute from the ocean and refurbished. SLS boosters carry no recovery hardware. They fall into the Atlantic and sink. Every component of the most powerful rocket ever built is destroyed on each flight. This is the architecture that costs $4.1 billion per launch. Above the core stage sits the interim cryogenic propulsion stage, built by United Launch Alliance, powered by a single RL-10 engine producing 24,750 pounds of thrust. This is the upper stage responsible for sending Orion toward the Moon. And here is the first counterintuitive fact about this rocket, one that reframes everything about why Artemis exists in its current form. Despite producing 15% more thrust than Saturn V, the Space Launch System can deliver only about 55% as much payload to the Moon. Saturn V could send approximately 49 metric tons on a trans-lunar injection trajectory. SLS Block 1 manages roughly 27. The reason is the upper stage. Saturn V's S4B third stage was a far more powerful instrument than the interim cryogenic propulsion stage. The consequence of this payload deficit is profound. Artemis cannot carry a lunar lander on the same rocket as the crew. Saturn V carried the command and service module and the lunar module together on a single launch. Artemis requires the lander, SpaceX's Starship human landing system, to launch separately on its own vehicle, reach lunar orbit independently, and wait for the crew to arrive. This single architectural fact explains more about the cost, complexity, and timeline of the Artemis program than almost any other detail. The spacecraft itself, Orion, which the Artemis II crew named Integrity, sits atop the rocket. It consists of 2 primary components. The crew module, built by Lockheed Martin, is 16.5 feet in diameter, 10.8 feet tall, and weighs approximately 8,500 kilograms. It holds 4 astronauts in roughly 316 cubic feet of habitable space, 30 to 50% more volume than the Apollo command module, which held 3. Behind it is the European service module, though designated ESM-2, built by Airbus Defence and Space in Bremen, Germany, under contract to the European Space Agency. This is the first time an international partner has built the critical path propulsion system for an American crew vehicle. The service module carries 8.6 metric tons of propellant and is powered by 33 engines, a single main engine refurbished from the Space Shuttle's orbital maneuvering system, 8 auxiliary thrusters, and 24 attitude control thrusters. 4 solar array wings, each 7 meters long, span a total of 19 meters and produce 11.2 kilowatts of power. The module contains components from 11 countries and approximately 12 kilometers of internal cabling. Orion's computing architecture represents perhaps the starkest generational leap from Apollo. Each of Orion's flight computers contains 128,000 times more memory than the Apollo guidance computer and runs 20,000 times faster at 75% of the weight of Apollo's single unit. Orion carries 2 redundant flight computers, each with 2 redundant modules, 4 computing systems in total compared to Apollo's 1. Over 1,200 sensors feed data to those computers in real time. The cockpit is a modern glass display system. Apollo astronauts read analog dials. But the component that matters most on this mission, the component that has generated more controversy, more internal debate, and more public dissent than any other element of Artemis II, is the heat shield. Orion's heat shield is 16.5 feet in diameter, and it is the largest ablative heat shield ever constructed for a crewed spacecraft. It is made of AVCOAT, the same ablative material used on Apollo, but the construction is fundamentally different. Apollo's heat shield was a monolithic fiberglass honeycomb with approximately 320,000 individually hand-filled hexagonal cells. Orion's shield consists of 186 pre-machined AVCOAT blocks bonded to a titanium skeleton and carbon fiber composite skin. During re-entry from lunar distance, this shield must withstand temperatures approaching 5,000 degrees Fahrenheit, roughly half the temperature of the Sun's surface, while the spacecraft slams into Earth's atmosphere at 25,000 miles per hour. On December 11, 2022, the Artemis I mission, an uncrewed test flight, brought Orion home from the Moon. The re-entry appeared successful, but when engineers examined the heat shield afterward, they found damage in more than 100 locations. Large chunks of AVCOAT had cracked and broken away rather than ablating smoothly as designed. The char loss was unexpected, it was significant, and it triggered an investigation that would delay Artemis II by years and divide NASA's engineering community in ways that have not fully healed. What they discovered was this. During Artemis I's skip re-entry, a maneuver where the capsule dips into the atmosphere, skips back into space, and then re-enters a second time for precision landing targeting, the heating rate decreased between atmospheric dips. That decrease allowed gas to accumulate inside the AVCOAT material, which did not have sufficient permeability to vent the pressure. The trapped gas cracked the charred surface layer and ejected pieces of the heat shield. A separate finding, documented in a NASA Office of Inspector General report from May 2024, revealed that 3 of 4 separation bolts embedded in the heat shield had melted through their thermal barriers. The cause was flawed NASA heating models that underestimated the thermal load. The Inspector General's language was direct. This failure mode could cause, and I am paraphrasing the official report, hot gas ingestion behind the heat shield, exceeding Orion's structural limits, resulting in breakup of the vehicle and loss of crew. And now consider what happened next. NASA chose to fly the Artemis II heat shield as is, not because the problems were solved, but because removing the heat shield would take years. The mitigation was a trajectory change. Instead of the skip re-entry used on Artemis I, Artemis II would perform a steeper, direct atmospheric entry. This reduces dwell time at peak temperatures and prevents the gas pressure build-up that caused the cracking. But there is a detail that has received remarkably little public attention. The Artemis II heat shield was manufactured to be even less permeable than the Artemis I shield. This was done to facilitate ultrasonic testing during production. Less permeable means less ability to vent gas, which is exactly the condition that caused the failure in the first place. NASA's own data showed that areas of the Artemis I shield, where the AVCOAT was naturally more permeable, did not experience cracking. Permeability was the fix. And the Artemis II shield moved in the opposite direction. NASA conducted over 1,000 trajectory simulations and 121 arc-jet tests to validate the new re-entry approach. An independent review team led by Wayne Hale, a former Space Shuttle flight director, concluded the modified trajectory was sound. In January 2026, NASA Administrator Jared Isaacman stated full confidence in the plan. 2 former astronauts who had expressed concerns met with the review team and, according to reports, appeared to accept the decision. But not everyone accepted it. Charles Kamada is a former NASA astronaut and heat shield expert who once served as Director of Engineering at the Johnson Space Center. When asked directly whether Artemis II was safe to fly, his answer was unambiguous. He said no. He called the decision crazy. That he compared it to the institutional failures that preceded the Challenger and Columbia disasters. His specific objection was that NASA had built what he described as toy models, simplified analytical frameworks not grounded in the full physics of the problem, and used them to justify a decision that had already been made. Dan Rasky, a NASA engineer, also believed astronauts should not fly with the current heat shield. On the other side, Danny Olivas, a former astronaut who served as a NASA heat shield reviewer, pushed back and called the risk acceptable. But his own characterization of what would happen during re-entry was striking. He acknowledged that the heat shield would crack. His argument was not that it would perform as designed. His argument was that the cracking would remain within survivable limits. Steve Scotty, from NASA's Langley Research Center, expressed confidence in the plan, but noted there was very little data available for analysis, and that the material itself changes its properties approximately every 20 seconds during re-entry. He classified the risk as moderate. Commander Wiseman, who is currently aboard the spacecraft as it returns from the Moon, stated publicly before launch that if the crew stuck to the new re-entry path NASA had planned, the heat shield would be safe to fly. The heat shield will face its definitive test on April 10th, when Orion enters Earth's atmosphere at approximately 25,000 miles per hour. What happens during those minutes will either validate NASA's analysis or confirm the fears of its critics. There is no simulation that substitutes for this moment. Jeremy Vanderkam, Orion's heat shield deputy manager, said it plainly in 2022. NASA's test facilities cannot reach the combination of heat flux, pressure, and shear stresses that an actual re-entering spacecraft experiences. They are always having to wait for the flight test. That flight test is happening now. The path to launch was not smooth. It was, in fact, a case study in the kind of grinding, expensive, iterative problem-solving that has defined the Space Launch System program from its inception. Artemis II was originally projected to launch between 2019 and 2021 during early program reviews. It did not launch until April 2026. The delays accumulated across years. By 2023, the target had shifted to November 2024. In January 2024, it was pushed to September 2025, driven by the heat shield investigation, battery issues, and life support system troubleshooting. In December 2024, outgoing Administrator Bill Nelson moved it again to April 2026. Between March and August 2025, it briefly moved forward to February 2026. Then the hardware began revealing its own timeline. On January 18, 2026, the fully stacked SLS rocket rolled out to Launch Pad 39B. Yet the wet dress rehearsal, a critical test where the rocket is fueled with cryogenic propellants and the countdown sequence is practiced, took place on February 2nd. It failed. A liquid hydrogen leak was detected at the tail service mast umbilical. Moisture had compromised Teflon seals at cryogenic temperatures. Hydrogen is the smallest molecule in the universe. It escapes through gaps that would stop any other element. At negative 423 degrees Fahrenheit, seals behave in ways that room temperature engineering does not always predict. This was not a new problem. The same location had leaked during Artemis I. The launch was postponed. A second wet dress rehearsal on February 19th succeeded. 2 days later, a helium flow anomaly was discovered in the interim cryogenic propulsion stage, and a dislodged seal inside a helium quick disconnect fitting had blocked the helium pathway. The rocket was rolled back to the vehicle assembly building. Repairs took roughly 2 weeks. The helium seal was replaced. Flight termination system batteries, flight batteries on the upper stage, core stage, and solid rocket boosters were all replaced. Launch abort system batteries were charged. On March 12th, the flight readiness review was completed. 7 two-hour launch windows were announced, April 1st through 6th and April 30th. On March 20th, the rocket rolled out to the pad a second time. On April 1st, at 6:35 p.m. Eastern, it left the ground. The total schedule slip from original projections to actual launch was approximately 5 to 7 years. The SLS program's first launch, Artemis I, had originally been targeted for December 2016. It flew in November 2022, 6 years late. The pattern is consistent. Now, what the mission actually accomplished once it was in space, because despite the controversy, despite the delays, despite the cost, Artemis II carried technology into deep space that did not exist during the Apollo era, and it tested that technology under conditions that no simulation can replicate. Within hours of launch, there was a problem. The spacecraft's toilet system, a $30 million assembly, malfunctioned. engineers on the ground walked the crew through a repair procedure. It was resolved. Minor in the grand scheme of a lunar mission, but a reminder that every system aboard Orion was facing its first crewed operational test. After reaching a highly elliptical Earth orbit with the ICPS upper stage, Victor Glover manually piloted Orion in a proximity operations demonstration, flying the spacecraft near the spent upper stage before it was disposed to a graveyard orbit. The ICPS also deployed 4 international CubeSats, Germany's Tackless, Argentina's Atenia, South Korea's K-Radcube, and 1 additional payload. Then the European service module fired its main engine for approximately 6 minutes, performing the translunar injection burn that sent the crew toward the Moon. The outbound coast took roughly 4 days. During those days, a technology that had never been tested from a crewed deep space vehicle began transmitting. The Orion Artemis II optical communication system, designated O20, is a laser communications terminal developed by MIT Lincoln Laboratory. It is approximately the size of a house cat, built around a 4-inch telescope mounted on a 2-axis gimbal. It transmits data via laser to ground stations at Las Cruces, New Mexico, and Table Mountain, California. The Australian National University also participated in a demonstration, attempting to receive signals using commercial off-the-shelf hardware rather than purpose-built NASA equipment. During Apollo, all communications between the spacecraft and Earth traveled via unified S-band radio. The maximum data rate was 51.2 kilobits per second. Television from the lunar surface was transmitted in slow scan format, 10 frames per second, 320 lines of resolution. The footage was historic. It was also, by any modern standard, barely watchable. O20 achieves a downlink rate of 260 megabits per second. That is approximately 5,000 times faster than Apollo's maximum capability. By day 4 of the mission, the system had downlinked more than 100 gigabytes of data, including the first 4K ultra-high-definition video ever transmitted from lunar distance. The implications extend far beyond Artemis. If the Australian National University demonstration succeeds, confirming that commercial hardware can receive deep space laser signals, it means future lunar communication ground stations do not require bespoke, multi-million-dollar NASA infrastructure. The cost of maintaining a permanent communication link with the Moon drops dramatically. This is the kind of advance that does not make headlines, but reshapes what is possible. And what you're about to hear next may reshape how you understand not just this mission, but the entire future of the Artemis program. Because while Artemis II was being prepared for launch, the program it belongs to was being fundamentally redesigned around it. On February 27, 2026, 32 days before Artemis II launched, NASA Administrator Jared Isaacman announced a sweeping restructuring of the Artemis program. The changes were not incremental. They were architectural. Artemis III, which had been planned for years as the mission that would return humans to the lunar surface for the first time since 1972, was redefined. It would no longer land on the Moon. Instead, Artemis III became a roughly 30-day mission in low Earth orbit, a rendezvous and docking exercise to test commercial lunar landers, including SpaceX's Starship human landing system and Blue Origin's Blue Moon, along with the new AVCOAT spacesuits. The mission profile was compared to Apollo 9, a critical systems test conducted in the relative safety of Earth orbit before committing to a lunar landing. The target date was set for 2027. The first crewed lunar landing since 1972 was pushed to Artemis IV. Target date 2028. A second landing, Artemis V, was also planned for 2028. Isaacman cited a warning from NASA's own Aerospace Safety Advisory Panel, which had flagged the original Artemis III plan as containing too many simultaneous first-time events, a new rocket configuration, a new upper stage, a new lander, new spacesuits, a new space station, and a lunar landing, all on a single mission. The restructuring separated those firsts across multiple flights. Then, on March 24, 2026, 8 days before Artemis II launched, Isaacman cancelled the Lunar Gateway. A gateway was a small space station that was to be assembled in lunar orbit, serving as a staging point for surface missions beginning with Artemis IV. Its 2 primary modules, the power and propulsion element, built by Maxar, and the habitation and logistics outpost, built by Northrop Grumman, had been in development for years. The European Space Agency had planned 3 additional modules. The Canadian Space Agency's Canadarm3 was being designed specifically for gateway operations. Isaacman's statement was direct. NASA was pausing Gateway in its current form and focusing on infrastructure that supports sustained operations on the lunar surface. In its place, he announced the Ignition Project, a $20 billion plan for a permanent lunar base to be built in 3 phases. Phase 1, from 2026 to 2028, that would focus on reliable lunar access and South Pole site scouting. Phase 2, from 2029 to 2031, would build semi-habitable infrastructure, including a pressurized rover contributed by the Japan Aerospace Exploration Agency. Phase 3, beginning in 2032, would establish a permanent human foothold, incorporating habitats from the Italian Space Agency and Canada's Lunar Utility Vehicle. The Gateway cancellation sent immediate shockwaves through the international partnership. The European Space Agency had invested years of planning and engineering into Gateway modules. ESA Director Joseph Ashbacher's public response signaled a potential shift in alignment. He stated that ESA wanted to increase the projects done in autonomy, where they are the masters of the decisions they take. The reports indicated that ESA was exploring expanded partnerships with India, Japan, and possibly China. The Canadian Space Agency's position was complex. The Canadarm3 contract, valued at $1 billion Canadian dollars, awarded to MDA Space in June 2024, had been designed for Gateway. MDA stated that the design had flexibility to pivot to an alternate operating environment, but Canada had already cancelled its small lunar science rover in February 2026 due to budget constraints. The Lunar Utility Vehicle program, targeted for 2033, was maintained. The program that Artemis II belongs to is not the same program that existed when its crew was announced. The architecture has changed. The destination of the next mission has changed. The space station it was meant to enable has been cancelled. The international partnerships that underwrote its design are under strain, and the budget picture is no less turbulent. Each Space Launch System mission costs approximately $4.1 to $4.2 billion. That figure comes directly from the NASA Office of Inspector General. When the program was authorized in 2010, the projected cost per launch was $500 million. The actual cost is roughly 8 times that estimate. The total SLS program expenditure has exceeded $60 billion. NASA's own senior officials told the Government Accountability Office that the program is unsustainable at current cost levels. Those are not the words of critics. Those are the words of the people running the program. That the booster and engine contracts alone, originally valued at $7 billion over 14 years, have grown to $13.1 billion over 25 years, $6 billion in overruns. Mobile Launcher 2, a new launch platform designed for a now cancelled upgraded version of SLS, ballooned from $383 million to a projected $2.7 billion, more than 70% of the overruns attributed to poor contractor performance by Bechtel. The Government Accountability Office found that production time for each successive SLS vehicle is increasing, not decreasing. The program is not becoming more efficient with experience, it is becoming less efficient. For context, SpaceX's Starship, the vehicle that will eventually serve as the Artemis lunar lander, currently costs approximately $100 million per test flight. Each SLS launch costs roughly 40 times more than a Starship flight. The Department of Defense stated in 2023 that it has no interest in SLS, as other vehicles already meet its needs at affordable prices. The roots of this cost structure are political, and they are well documented. When Congress authorized the Space Launch System in 2010, the legislation mandated the use of Space Shuttle-era components, RS-25 engines, 5-segment solid rocket boosters, shuttle-derived tooling and the manufacturing infrastructure. This decision locked in contractors, locked in facilities, and distributed work across congressional districts that had supported the shuttle program for decades. But the rocket was designed, in significant part, around the preservation of existing jobs and contracts, rather than around optimal engineering. Laura Forczyk, the founder of the space consulting firm Astrolytical, described it directly. SLS contracting is set up to spread federal funding around to districts important to supporting members of Congress, not to produce a rocket in the most efficient way possible. Eli Dorado of the Center for Growth and Opportunity called SLS an irredeemable mistake driven by pork barrel politics. Former NASA Administrator Charlie Bolden predicted that SLS would eventually go away because commercial entities would catch up. In 2019, a former employee of United Launch Alliance alleged that Boeing had blocked investment in orbital refueling technology specifically because it would undermine the case for SLS. The program's critics call it the Senate Launch System. The name is not affectionate. The political dynamics around SLS in 2026 are contradictory in ways that border on absurd. The Trump administration's fiscal year 2026 budget proposal called SLS grossly expensive and 140% over budget, and proposed cancelling it after Artemis III. Congress responded with the One Big Beautiful Bill Act, signed on July 4, 2025, which added approximately $9.9 to $10 billion for NASA, explicitly preserved SLS and Orion beyond Artemis III, and mandated at least 4 additional SLS missions. Casey Dreyer of the Planetary Society described it as the fastest repudiation of a White House budget proposal he had witnessed. Yet then Administrator Isaacman cancelled Gateway anyway, a program that Congress had just funded at $2.6 billion. Whether this cancellation conflicts with the congressional mandate remains unresolved. The fiscal year 2027 budget proposal, released approximately April 5, 2026, proposed cutting NASA's budget again to $18.8 billion, with $8.5 billion for Artemis and a nearly 50% reduction to the science budget. Congressional pushback is expected. Again, this is the institutional reality surrounding the mission currently in flight. 4 astronauts are returning from the moon inside a vehicle that costs more per flight than the entire annual budget of most national space agencies. The rocket that launched them uses engines designed for a program that ended in 2011. They are under contracts that have overrun their original estimates by billions of dollars, built to requirements dictated not by engineers, but by legislators. And the next mission in the sequence, Artemis III, has been redesigned so thoroughly that it will not go to the moon at all. There is a tendency, when discussing Artemis, to separate the engineering achievement from the institutional reality, to celebrate the mission while setting aside the context. But the context is inseparable from the mission. The heat shield decision, the cost overruns, the political mandates, the international strain, these are not footnotes. They are the conditions under which 4 human beings were sent farther from Earth than anyone in history. And what those 4 human beings experienced on April 6, 2026, deserves to be understood on its own terms. The lunar flyby lasted approximately 7 hours. As Orion swung behind the far side of the moon, the crew lost all contact with Earth for roughly 40 minutes. No radio signal can bend around a celestial body. For those 40 minutes, the 4 members of the Artemis II crew were more isolated from the rest of humanity than any human beings have ever been, farther away, with no communication link, traveling at approximately 60,863 miles per hour relative to Earth. At closest approach, Orion passed roughly 4,067 miles above the lunar surface. This is a paradox worth sitting with. Artemis II came within 4,000 miles of the moon. Apollo missions that landed on it traveled to 0 miles, even Apollo 13 on its emergency flyby. Yet the mission that held the previous distance record passed within 158 miles. Artemis II was 25 times farther from the moon at its closest point than Apollo 13 was at its closest. And yet, Artemis II set the record for the farthest any human has been from Earth. The geometry of orbital mechanics does not always align with intuition. During the flyby, the crew witnessed something that no living human had ever seen from that vantage point. As the spacecraft passed behind the moon, the sun was eclipsed by the lunar disk, a total solar eclipse observed from beyond the moon itself. Jeremy Hansen described the entire moon as glowing, corona light extending easily 10 diameters of the sun around the entire lunar surface. The crew also observed Earthrise, the same phenomenon that Apollo 8 astronaut William Anders captured in the photograph that became one of the most reproduced images in human history. Except the Artemis II crew saw it in 4K resolution, transmitted to Earth via laser at 260 megabits per second. There are reports, not yet fully confirmed, that the crew may have observed a meteor impact on the lunar surface in real time during their eclipse observation. NASA's lunar science lead, Kelsey Young, stated that teams on the ground were jumping up and down at the data. The crew proposed naming 2 lunar craters, Integrity, after their spacecraft, and Carroll, after Commander Wiseman's late wife. The proposals will be submitted to the International Astronomical Union. One additional moment from the flyby carries particular weight. Before the mission, Jim Lovell, the commander of Apollo 8 and Apollo 13, the man who held the previous distance record, who had seen Earthrise for the first time in 1968, recorded a special message for the Artemis II crew. Lovell passed away in 2025. His message was played during the mission. The details of what he said have not been fully released, but the arc is unmistakable. The man who flew the farthest, on the mission that nearly killed him, leaving his voice aboard the spacecraft that finally went further. On Flight Day 7, Orion exited the Moon's sphere of gravitational influence and began the return coast toward Earth. The crew conducted a ship-to-ship call with the astronauts aboard the International Space Station, one crew in low Earth orbit, at another returning from the Moon. NASA transmitted what it described as the longest person-to-person email ever sent in human history, from mission control to the crew at lunar distance. On Flight Day 8, the crew performed a demonstration that had never been attempted with humans in actual deep space. They constructed a radiation shelter inside the Orion cabin, using stowed equipment and supplies within 30 minutes. This was not a drill. It was a validation of a protocol that may one day save lives. Beyond the protection of Earth's magnetic field, solar particle events can deliver lethal doses of radiation. Apollo flew during a period of solar minimum, and even so, a massive solar storm in August 1972 between Apollo 16 and Apollo 17 would have posed a grave threat to any crew in deep space at the time. Artemis II flew during a period of elevated solar activity. The spacecraft carries 6 Hera radiation sensors at various cabin locations, crew-worn active dosimeters, and 4 upgraded German M42 EXT detectors with 6 times more resolution than those flown on Artemis I. NASA and NOAA maintained 24-hour solar monitoring throughout the mission. The radiation environment is one of the clearest areas where Artemis goes where Apollo genuinely could not. Apollo had no real-time radiation monitoring, no sheltering protocol, no radiation-hardened electronics. Orion has all 3. The Artemis I uncrewed test flight carried 2 mannequin torsos, Helga and Zohar, equipped with 5,600 passive sensors and 34 active detectors. One torso wore an Astrorad radiation vest. And the data confirmed that the vest reduced organ-level radiation doses through the Van Allen belts. This was the first time such measurements had been taken in deep space with anatomically realistic phantoms. The science aboard Artemis II extends beyond radiation. The Avatar project, a set of organ-on-a-chip experiments, carries bone marrow chips derived from each crew member's own biology. These will be compared against Earth-based twin chips and pre-flight and post-flight blood samples. It is the first time individual astronaut biology has been tracked this precisely in deep space. The ArchER system monitors crew health metrics in real time throughout the mission. These are not headline-grabbing payloads. They are the foundation of everything that comes after. Every lunar surface mission, every Mars transit study, every long duration the deep space habitat depends on understanding what happens to human biology beyond Earth's magnetosphere. Artemis II is producing that data with living subjects for the first time in more than half a century. There is one more dimension of this mission that deserves its own examination: the gap between what the crew lived inside for 10 days and what Apollo crews endured for similar durations. Because the technological distance between the 2 spacecraft is not merely a matter of computers and communications. It is a matter of what it means to be a human being in a machine, 250,000 miles from help. Apollo astronauts inhabited the command module, a pressurized volume of roughly 218 cubic feet, shared among 3 men. There was no exercise equipment, there was no galley. Waste management was primitive, relying on bags that were, by every account from every crew that flew, among the most unpleasant elements of the entire mission. Meals were reconstituted freeze-dried food or thermostabilized pouches. There were no private spaces. Sleeping arrangements were improvised. The temperature fluctuated. Noise was constant. The command module worked. It kept its crews alive. But it was, by any standard, a survival capsule, not a habitable environment. Orion's crew module provides 316 cubic feet of habitable volume for 4 astronauts, roughly 50% more total space with 1 additional crew member. It contains a functioning galley with 189 unique menu items and 10 beverages. There is a flywheel exercise system, important for mitigating the bone and muscle loss that begins within days of entering microgravity. The waste management system, the same $30 million system that malfunctioned on day 1, is, when functioning, a generation beyond what Apollo offered. Noise and odor mitigation systems are built into the environmental control architecture. There are provisions for crew privacy. None of this is incidental. It is foundational. Short missions can tolerate discomfort. Long missions cannot. If humans are to spend 21 days in Orion undocked from any other structure, or eventually 6 months docked to a lunar orbital platform, then the vehicle must be more than a survival capsule. It must be a place where human beings can function, rest, and maintain cognitive performance under conditions of extreme isolation and stress. Artemis II is the first crewed test of whether Orion achieves that threshold. The abort system is another area where the distance between eras is not incremental, but categorical. During Apollo, if something went catastrophically wrong during the first minutes of launch, the launch escape system, a solid fuel tower mounted above the command module, would fire and pull the capsule away from the failing rocket. It was a passive system. The escape trajectory was controlled by fixed canards, small aerodynamic surfaces that deployed to orient the capsule. The solid rocket plumes exhausted from nozzles near the bottom of the tower, close to the capsule itself. It worked. It was never needed on a crewed Apollo flight, though it was proven on uncrewed tests, but its design left limited margin for complex failure scenarios. At Orion's launch abort system stands 44 feet tall and contains 3 solid fuel motors. The abort motor alone produces 400,000 pounds of thrust. But the critical difference is control. The system uses 8 independently modulated variable thrust steering nozzles that can respond in milliseconds. The nozzles are reverse flow. They direct exhaust plumes away from the capsule rather than toward it. The system is actively controlled, meaning it can adjust its escape trajectory in real time based on the specific failure it is responding to. NASA designed the system to be 10 times safer during ascent and re-entry than the Space Shuttle, a vehicle that was lost twice during those phases, killing 14 crew members. On April 1st, as SLS climbed through the atmosphere, the launch abort system sat atop Orion for the first time with a crew beneath it. It was not needed. It was jettisoned as planned once the vehicle reached sufficient altitude. But its presence represented a design philosophy that Apollo's engineers would have recognized in principle while marveling at its execution. Always give the crew a way out. Build the way out so that it works even when nothing else does. The European service module adds another layer to the comparison. Apollo's service module was built entirely by North American Rockwell, an American contractor for an American program. Orion's service module was built by Airbus Defence and Space in Bremen, Germany, with components from 11 countries under contract to the European Space Agency. It is derived from the Automated Transfer Vehicle, ESA's unmanned cargo craft that serviced the International Space Station. It contains 20,000 parts, 12 kilometers of cabling, and Kevlar shielding against micrometeoroids. Its main engine is a refurbished Shuttle Orbital Maneuvering System engine, another piece of Space Shuttle heritage, repurposed for a new mission and a new era. The fact that the propulsion system keeping 4 American and Canadian astronauts alive on the way home from the Moon was designed, built, and tested in Europe is itself a statement about how spaceflight has changed since Apollo. In the 1960s, the space race was a bilateral competition between 2 superpowers. In the 2020s, it is a multinational collaboration held together by treaties, trade agreements, and shared cost burdens, a collaboration that, as we discussed, is now under significant strain. There is a question that runs beneath this entire mission, and it is time to address it directly. Because the title of what you are watching, Artemis II Goes Where Apollo Couldn't, is true. But truth requires precision, and precision requires acknowledging what Artemis II cannot do that Apollo did. Apollo landed on the moon 6 times between 1969 and 1972. 12 human beings walked on the lunar surface. They drove a rover. They deployed scientific instruments that transmitted data for years. They brought back 842 pounds of lunar samples that scientists are still analyzing today. They did this with computers that had less processing power than a modern pocket calculator, but with a heat shield made by hand-filling 320,000 honeycomb cells, with no abort option once the lunar module descended below a certain altitude. Artemis II flew past the moon at 4,000 miles. It did not orbit. It did not land. It carried no lander. It could not carry a lander because the rocket that launched it does not have the payload capacity to send both a crewed spacecraft and a landing vehicle to the moon on a single flight. That is not a temporary limitation. It is a defining characteristic of the SLS Block 1 architecture. And as of February 2026, the upgraded versions of SLS, Block 1B and Block 2, which were designed to increase payload capacity with a more powerful exploration upper stage, have been permanently cancelled. NASA will standardize on Block 1 with a Centaur 5 upper stage. The payload growth path that was meant to close the gap with Saturn V no longer exists. This means that for every future Artemis landing mission, the lunar lander must launch separately on a commercial vehicle, reach the moon independently, and wait in lunar orbit for the crew to arrive aboard Orion. The lander selected for Artemis IV, the first planned landing, is SpaceX's Starship human landing system. To deliver Starship HLS to the moon, SpaceX must first demonstrate something that has never been done: multiple orbital refueling flights to fill the vehicle's tanks in low Earth orbit before it departs for the moon. As of April 2026, Starship is still in its test flight phase. Elon Musk stated on April 3, 2026, that the next test was 4 to 6 weeks away. Yet the Starship HLS must also complete an uncrewed lunar landing demonstration before it carries astronauts. Artemis IV is targeted for 2028, but the new Mobile Launcher 2, required for the mission, is not projected by the NASA Inspector General to be ready until spring 2029. This creates an inherent schedule conflict that has not been publicly resolved. The program's track record does not inspire confidence in aggressive timelines. The original goal, set in 2017, was to land humans on the moon by 2024. The current target is 2028. That is already 4 years behind. Isaacman's stated ambition of launching an Artemis mission every 10 months is unprecedented. NASA has never achieved less than approximately 3 years between SLS launches. None of this diminishes what Artemis II accomplished. It contextualizes it. Artemis II went where Apollo could not, in the literal sense that it traveled farther from Earth than any crewed mission in history. It communicated at speeds that Apollo could not have conceived of. It monitored radiation in ways that Apollo had no instruments to attempt. It carried 4 crew members where Apollo carried 3. It tested life support systems designed for 21 days of independent operation compared to Apollo's 14. It demonstrated an abort system that is actively controlled with 8 independently modulated thrust nozzles compared to Apollo's passive canard-based escape tower. Orion's launch abort system produces 400,000 pounds of thrust with millisecond response time. It is designed to be 10 times safer during ascent and re-entry than the Space Shuttle. Artemis II also went where Apollo could not, in the sense that it is a product of an era Apollo did not have to navigate. 53 years of shifting political priorities, 53 years of competing budget pressures, 53 years of institutional caution built on the memory of Challenger and Columbia, 53 years during which no one was asked to accept the risks that Apollo crews accepted as routine. The Apollo program spent approximately $25 billion in 1960s currency, roughly $200 billion in today's dollars, over the course of a decade, with a singular national mandate and Cold War urgency driving every decision. Artemis has no equivalent mandate. It has cost-plus contracts, congressional earmarks, rotating administrators, annual budget threats, and a public whose attention shifts between missions. Apollo could not do what Artemis II did. But Apollo could do something that Artemis, 13 years and more than $60 billion into its existence, has not yet done. The gap between those two facts is the story of American spaceflight in the 21st century. As of today, April 9, 2026, the Artemis II crew is on Flight Day 9 of their mission. Tomorrow, they will face the moment that no simulation can replicate. Orion will hit Earth's atmosphere at approximately 25,000 miles per hour. The heat shield that cracked in more than 100 places on Artemis I, the heat shield that was made less permeable than its predecessor, and the heat shield that some of NASA's own engineers said should not fly, will endure temperatures approaching 5,000 degrees Fahrenheit. The re-entry will use a modified direct entry rather than the skip re-entry that caused the damage on Artemis I. 1,000 trajectory simulations say this will work. 121 arc jet tests say this will work. An independent review board, led by a former shuttle flight director, says this will work. But the deputy manager of Orion's heat shield program said it himself. NASA's test facilities cannot reach the combination of heat flux, pressure, and shear stresses that an actual re-entering spacecraft experiences. They are always having to wait for the flight test. The flight test is tomorrow. If it succeeds, and the expectation supported by extensive analysis, it is that it will, then Orion splashes down in the Pacific Ocean off San Diego at approximately 8:07 p.m. Eastern Time on April 10th. The USS John P. Murtha will be waiting. Recovery teams have trained for this since at least March 2025, including a full-scale underway recovery test aboard USS Somerset off the California coast. Divers will enter the water, the capsule will be secured, a hatch will open, and Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen will breathe unfiltered ocean air for the first time in 10 days. They will become the first humans to return from lunar distance since the crew of Apollo 17 in December 1972, 53 years and 4 months. In that time, the youngest person to walk on the moon, Harrison Schmitt, who was 37 when he stepped onto the surface during Apollo 17, turned 91. And most of the Apollo astronauts who traveled to the moon are gone. Jim Lovell, the man whose record Artemis II broke, is gone. The world they launched from no longer exists. The world they are returning to is still deciding whether it wants to go back. The heat shield will be recovered, it will be examined, and what engineers find on its surface will determine not just the future of Artemis, but the credibility of the analytical models that NASA used to justify this flight. If the direct entry profile eliminated the cracking, then the path forward for Artemis III, IV, and beyond becomes clearer. A redesigned heat shield with improved AVCOAT permeability is already planned for Artemis III and subsequent missions. If the shield shows unexpected damage, if the models were wrong again, then the program faces a reckoning that will make the current controversies look minor. There is no middle ground on re-entry. The physics does not negotiate. Consider what this mission represents in totality. 4 human beings strapped into a spacecraft that has never before carried a crew, launched atop the most powerful rocket ever flown, on a trajectory that took them farther from their home planet than any member of their species has ever been. They flew past the moon at 60,000 miles per hour. They watched the sun disappear behind the lunar disk. They saw Earth from a distance that reduced it to something a hand could cover. They transmitted 4K video across 250,000 miles using a laser the size of a house cat. They built a radiation shelter from stowed supplies in 30 minutes. They carried chips of their own bone marrow in a miniature laboratory. They did all of this in a spacecraft with a heat shield that their agency knew was imperfect, under a program whose architecture was being redesigned around them, funded by a budget that their own government described as grossly expensive. They went anyway. That is not a triumph uncomplicated by reality. It is a triumph inseparable from reality. Artemis II is magnificent and troubled and overdue and necessary, all at the same time. The rocket costs too much. The program has taken too long. The heat shield should have been better. The political infrastructure that sustains it is fragile and contradictory. All of these things are true. And it is also true that on April 6, 2026, 4 people saw Earthrise from farther away than any human being who ever lived, and sent the image home in resolution so sharp you could see weather systems moving across the Pacific. The last time a human being left low Earth orbit was December 19th, 1972. Eugene Cernan climbed into the Apollo 17 command module, and the hatch closed, and for 53 years no one followed. In that half-century, humanity built the International Space Station, launched the Hubble and James Webb Space Telescopes, landed rovers on Mars, mapped the cosmic microwave background, detected gravitational waves, and sequenced the human genome. We sent robots to the outer solar system and peered back to within 300,000 years of the Big Bang. We did not go back to the moon. Not because we lost the technology, not because we lost the will, but because we never rebuilt the institutional consensus required to sustain the cost and accept the risk. 5 separate presidential administrations directed NASA to return to the moon. The Constellation program was authorized, partially built, and cancelled. The Space Launch System was authorized in its place, under different requirements, with different contractors, carrying different political obligations. The original target was a test launch by 2016 and crewed flights by the end of the decade. The test launch happened in November 2022. The crewed flight happened in April 2026. Every deadline slipped, every budget grew, every review uncovered new problems that required new timelines and new funding. During those 53 years, the average age of a NASA engineer rose. The workforce that built Apollo retired. The institutional knowledge of what it actually takes to send humans beyond low Earth orbit, the 1,000 small decisions, the engineering intuitions, the operational reflexes, had to be rebuilt from technical documentation and the memories of a shrinking pool of veterans. Artemis II is not just a test of hardware. It is a test of whether an agency that has not done this in half a century still can. The early evidence suggests that it can, imperfectly, expensively, contentiously, but it can. Artemis II did not rebuild that consensus. It flew without it. It flew on a budget under annual threat of cancellation. It flew with a heat shield its own engineers debated. It flew while its program was being restructured in real time. It flew because at some point, after 53 years, the only way to test whether we can still do this was to do it. Tomorrow, the heat shield answers. And after that, the question is no longer whether we can send humans to the moon. The question is whether we will choose to keep going, and whether the architecture, the budget, the partnerships, and the political will exist to turn a 10-day flyby into something permanent. The moon is 239,000 miles away. We have now proven again that we can reach it. What remains to be proven is whether reaching it was the hard part. It was not.